Hello everyone. So this is our video presentation for ground mounts in electrical circuits project assignments for the subject of electromagnetic interference and compatibility. Talking about main issues which we face in EMIC are three. Number one is signal integrity, number two power integrity, and three EMC, which is electromagnetic compatibility. Under these three major issues, there are a set of six problems in this field. And out of which one important problem is ground and power bounds. In this particular presentation, we are going to talk about ground bounds. Ground bounds is nothing but a special case of crosstalk, which is an unwanted noise in a signal path, and it is due to the capacitive and inductive coupling between two nets. There are various types of crosstalks, as we can see from the report, and the formula for the ground mounts, whenever there is a return path in a particular system, is depends on total inductance of the system and the rate of change of current. Now, to decrease ground mounts voltage noise, there are two particular ways. One is to decrease the partial self-inductance of return path by using short lengths and wide interconnects, or to increase the mutual inductance of the two legs, that is the signal path and the return path, by bringing the current signal path and the return path much closer. Now in this particular assignment, we are trying to reduce the total inductance so that we can understand the effects of the ground mounts here. Ground mounts also depends on the geometry of the transmission lines used, and it is always suggested to use uniform transmission line to have less cases of ground mounts. This is a particular example of ground mounts here, which we can see. Uh,
Coming to the practical application of the ground transmission line theory and observing the ground bounces in different circuits. Here we took a circuit and simulated the circuit using the ANSYS software. So here we can observe the circuit which has a source voltage, uh, which is a pulse voltage, a transmission line whose impedance is 50 ohms and time delay is 0.1 nanoseconds, and here is a load component in which in the first case we took the load component as resistor, in the second case we took the load component as inductor, and in the third case we took the load component as capacitor. By changing the values of each component, we have observed the graphs and their reflections accordingly. Here we can observe, as the first graph, we took the load resistor value as 50 ohms. Here we can observe the graph as the red line and the green line are the input and output voltage disturbances. Here we can see that almost there is negligible change. This preferably shows that there is negligible effect of the resistor value of 50 ohms. By increasing the resistor value to 150 ohms, we can observe a few deflections here in the graph accordingly. This shows that as the resistor value increases, there will be a few deflections because of the voltage drop, which is also known as ringing effect in the circuit for the transmission line. Here, as the voltage, as the resistor value increased to 200 ohms, we can observe similar kind of reflections, which same as in the case of 150 ohms. But when we observe correctly, there is an increase in the voltage value, that is the peak value of the graph. Here it is 750 ohms and here it is 700 ohms. This shows that as the resistor value increases, the peak value of the voltage final graph also increases. The same is observed here also in the case of 500 ohms and 1000 ohms. That is, the regular reflections of the graph is similar, but the peak value of the graph changes. So this shows that there is a negligible effect of the resistor value and the resistor change for the ground bounce effect. Okay, changing the component from resistor to inductor. Here we have observed a different change of graphs. Here we took the inductor value as 5 microhenry. And this is the resulting graph. Here we have observed few deflections and an increase in the voltage value. And when we change the value from value of the inductor from 5 microhenry to 1 nanohenry. This is the graph we have observed. Here we can observe a drastic change in the graph. And when we change the value from 1 nanohenry to 5 nanohenry, this is the graph we have observed. When we observe the above and the below graphs, those are both are the similar graphs almost, and which only change we have observed is the amplitude change of the result output graph. And when we come to this graph, here the load inductor value is 5 picohenry. Here we can observe like the negligible effect of the ground mounts. So the analysis which we did using these graphs is that as the inductor value decreases, there will be zero effect of the inductor on the ground bonds in the transmission line. So coming to the capacitor, here the load component is changed from inductor to capacitor. In the first case, we took the capacitor value as 0.5 picofarad. Here we can observe a few deflections because of the capacitor. So changing the value of capacitance from 0.5 picofarad to 1 picofarad, this is the change we have observed. Like almost 0.5 picofarad and 1 picofarad has similar graph, only the amplitude value changed. So when we increase the value from 1 picofarad to 100 picofarad, here we can observe like negligible change, which is almost zero in the graph. That is, this shows that as the capacitance value increases, the ground bonds effect decreases on the entire circuit of the transmission line theory. These are the conclusions which we have drawn from the graphs, and this is an explanation which we have observed using the ANSYS software by practical application.
The problems which we face due to the ground mounts are generally two. One of them is the fault switching. Now this may occur when the die ground or the die VCC reference voltage bounces enough to cause input toggle point of the die to shift enough to pass through a guaranteed threshold. Now we can see from the graph the input voltage switches here, and we can see due to this switching effect, due to this sudden change or the switching effect, we can see that there is a peak value which we can see, which we observe. So here there is a rise here in the voltage. So what happens is that generally a noise is created in the victim line as a decrease in the peak, we can see here, and whenever there is a fall, we can see there is a rise in the victim line. Also, because of this ground mounts, obviously the second effect which we face is the poor signal quality, which is the first effect which a designer will see from any design. Now if a particular design is bouncing and ringing, then the noise will extend directly to the output and into the signal path, and this might also get enhanced if the transmission line is inductive, and because the inductive always kicks the peaks and valleys of the noise. Now there are various methods for decreasing. These are some of the methods which we suggest. It is to use decoupling capacitors to localize ground bounds, use resistors to limit current flow, use routing to reduce inductance, choose ICs with slower rise and fall times, prevent simultaneous switching whenever possible, and keeping the decoupling capacitor switching whenever possible. Thank you.